Okay, welcome to the last chapter in dynamics. It's gravitation, and it's really Newton's law of gravitation that we're trying to quantify here. And you know, gravity is so fundamental, and it seems like that's something we should have started with. You know, because in real life, Newton's theory of forces really stemmed from his pondering of gravity. So, you know, it seems like why didn't we start with teaching you gravity? And really, the reason is because to fully appreciate gravity, we had to we needed knowledge of circular motion first. So we had to sort of get to circular motion, and then now that we have circular motion, we move on to gravity. So I'll just jump right to it. Newton's law of gravitation is this formula. It's capital G, which is a universal constant. It's something that is just, you can look up in a textbook. It has a certain value, and it's the same value whether it be on Earth, on the Moon, and Jupiter, somewhere else in the universe completely. It's just a universal constant times mass 1, mass 2 over r squared, where and this calculates the force of gravity between any two objects. So those two objects could be the Earth and myself, the Earth and a chair. But the real beauty of this equation is this says if you have mass, you can distort the gravitational field, meaning if you have mass, you can exert gravity on another object. You can attract another object. So really what Newton's law of gravity says is it doesn't have to be the Earth. Earth is not the only thing that can exert gravity. You know, this could be, say, like me, and this could be, say, like my cat. You know, my cat has a smaller mass than me, technically. That's what that says. And I can calculate the force of gravity between myself and my cat. It's going to be capital G times the mass of me times the mass of my cat divided by r squared, where r squared is the distance between myself and my cat, or the distance between the two objects. So it's a pretty simple formula, quite honestly. The take-home message is that any object that has mass will exert a force of gravity on surrounding objects. So you might be wondering, well, why haven't I noticed that? Why am I only learning about this now? Let's actually think about that for a second. For the record, the universal constant G has that value, 6.674 times 10 to the minus 11. That's important. So if you're wondering why you haven't noticed the force of gravity on, you know, between you and other people, then I don't know why I can't insert space here. OneNote is not listening to me. Okay, well, we're going to make do with the space that we have then. So here's an example. Are you having trouble finding a partner? You know, you can't find a significant other. You can't even find a date. Maybe physics can help you. Maybe physics can help you explain why you aren't able to attract other people. So, you know, force of attraction, ha ha ha, funny joke. So let's calculate the force of gravity between, say, two people. Well, the force of gravity is going to be G times the mass of person 1 times the mass of person 2 divided by the distance between the two people squared. So let's kind of order of magnitude estimation here. G is 6.67 times 10 to the minus 11. Let's say, I don't know, let's say the first person is 60 kilograms. Let's say the second person is 80 kilograms. And I don't know, let's say you're on a date with someone. How far away are you sitting from them? I don't know, like a meter, meter and a half? Let's say a meter. Okay, order of magnitude estimation here. We don't need calculators. 6.67 times 10 to the minus 11. Let's round that to 10. So 10 times 10 to the minus 11. 60 This is going to be a bit of a big round, but that's okay. Let's round 60 to 100. Let's round 80 to 100, because why not? And a meter squared is simply just 1, so that's nice and easy. Okay, 10 times 10 to the 11, or 10 to the minus 11 is 10 to the minus 10. 100 times 100 is 10 to the 4. So this is going to be 10 to the minus 6 newtons. 10 to the minus 6 newtons. The reason why you don't notice the force of gravity between you and other objects is because your mass is so small that the amount of gravitational force that you're pulling with is on the order of magnitude of 6 decimal places. 6 decimal places, that's how small it is. So that's why you don't notice it. Now, just because you don't notice it doesn't mean it doesn't happen. Now, I mentioned the other day that, when we did the force of gravity in the previous questions, mg, I said that comes out of Newton's law of gravity. Let's kind of see where that happens. So we say that, we notice that at the Earth's surface, the acceleration is constant. And overall, we know this isn't true for gravity, because we know Newton's law of gravity says the Newton's law of gravity is a function of distance. So we know if we get farther away from an object, the force of gravity decreases. But we know that near the Earth's surface, meaning an apple at the top of a tree will feel the same amount of force of gravity as me standing under the tree. So if you're near the Earth's surface, we can approximate the force of gravity to be constant, and this can be verified experimentally. So we say, okay, the force of gravity we know is going to be the object's mass m times some unknown gravity g. Now, where does that value come from? I've been using 9.8, 9.8, 9.8, but where does that 9.8 come from? Well, if you equate this to Newton's law of gravity, g, mass of the Earth, mass of the object, divided by the distance between the two objects squared. Now notice the distance between the two objects, it's from the centers of the object. So if I'm standing on the Earth's surface, the distance between me and the Earth is not 0. It's the distance between the center of the Earth and me. So this is going to be the radius of the Earth. Now, here's where things get fun. Why is this just a constant? Well, whether we're talking about me object or you object or chair object or apple object, right? This is the variable. M object is the variable. Mass of the Earth is constant in all of these scenarios. What's the force of gravity between me and the Earth? What's the force of gravity between you and the Earth? What's the force of gravity between the apple and the Earth? The thing that's constant in all of those scenarios is Earth. So this is constant, and G is constant in all of those scenarios. So we actually say mass object times G is going to be the same as capital G mass of the Earth over radius of the Earth squared times mass of the object. So using Newton's law of gravitation, you can actually see that little g is equal to capital G times mass of the Earth over radius of the Earth squared. And I encourage you for homework to look up mass Earth, radius of the Earth, and verify that G in fact equals 9.8. So you can do that quite easily. You just do capital G, which I've given you above, times mass of the Earth divided by radius of the Earth squared, and you should in fact equal 9.8. Okay, that's pretty much all there is for Newton's law of gravity. There is a neat implication though, and I know we're 7 minutes over time, so please bear with me. I am almost done, I promise. There is a neat implication though with Newton's law of gravity, and it actually explains orbits, and not just orbits of satellites, but also orbits of, say, like the moon. And we know the moon is actually in an orbit around Earth, and we know the moon doesn't fall in towards Earth, right? It circles Earth. So let's actually figure out kind of some properties of well, space physics, or satellite physics. So why does the moon not fall? Well, again, this is a forces question, so let's draw a free body diagram of the moon. We have the Earth, we have the moon. The moon travels mostly in a circular orbit around us. So this is why we needed circular motion first before doing this. And the only force acting on the moon is the force of gravity between the Earth and the moon. Common misconception is people think that in space there's no gravity. That's completely false. There's absolutely gravity in space. We feel weightless in space because there's no normal force, but there's gravity. There's definitely gravity in space. So if you draw a free body diagram of the moon, there's really only one force. It's just gravity. There's no friction, there's no normal force, it's just gravity. So F net equals ma. I know the trajectory is circular motion, so it's going to be centripetal A, and the net force is gravity. So in this case, gravity is causing circular motion. We've seen previously, in the previous video, we saw normal force, friction, tension cause circular motion. Now we're seeing gravity cause circular motion. And using Newton's law of gravitation, we can say the force of gravity is G, mass of the moon, times mass of the Earth, divided by, I'll say the, well, r, the distance between them, squared, equals mv squared over r. And simplifying things a little bit, I can cancel one of the r's. I can cancel the mass of the moon, which is kind of interesting. And where does that leave me? It leaves me with v squared equals gm Earth over r. Okay, this is the orbit, the radius of the orbit from the center of the Earth. And that means the speed of the moon is going to equal the square root of capital G, mass of the Earth, divided by the radius of the orbit. So we know what how far the moon is away from the surface of the Earth, and we know we know the radius of the Earth itself. So if you add those two, the radius of the Earth plus the orbiting radius, you'll get the total r value. And you know G is a constant, mass of the Earth is a constant. So you can actually solve for the speed at which the moon is orbiting the Earth, which is kind of really, really cool. And what you can do with that is you can extrapolate and say, what kind of speed would any satellite, whether it be a Rogers satellite, a Telus, a Bell satellite, a telecommunications satellite, the International Space Station, what speed would an object need to have in order to properly orbit the Earth in a stable orbit? And if anything's traveling under that speed, it'll fall back to Earth. So it's actually this equation here that explains why when you throw a ball, like you're just throwing a ball to your best friend, that's why the ball doesn't orbit the Earth, right? You're clearly throwing the ball at a speed less than the orbiting velocity. So it's just in a decaying orbit. It'll just come back to the Earth's surface. So luckily the moon is not in a decaying orbit. Luckily the moon is traveling at exactly the right speed to be in a stable orbit. And thinking even bigger than that, the Earth is revolving around the sun. It is a complete fluke that the Earth has just the right amount of velocity to be in a stable orbit around the sun. And not just the Earth, all the other planets. All the other planets are in a stable orbit around the sun, meaning they have just the perfect amount of velocity, given the mass of the sun and the radius away they are from the sun, to be in stable orbits. So, I mean, to think about, the universe and the physics of the universe, the Earth is the way it is. It's incredibly rare, and it's so unlikely, which is why religion has tried to tie in this notion of a deity, saying, oh, it's so unlikely to have happened by nature, it must have been done by some sort of deity. And another viewpoint would be, if you look at how many stars there are in our entire universe, and how many planets there are in this entire universe, there's this notion of the law of large numbers. I mean, there are so many other planets that are not in stable orbit, so they collide with other things and they break apart into little asteroids, and or they get eaten up by black holes, or they get eaten up by stars. Like the law of large numbers is, if you have enough of something, eventually you're gonna hit every single scenario. So Earth just happens to be, there's just so many planets out there and so many stars that Earth just happens to be the planet that has all the right conditions. And some might believe that it was a deity made that happen, and some might believe, like, law of large numbers. You have so many different data points that one of them was statistically bound to have all the right conditions. So anyway, that's kind of an implication of Newton's law of gravity. It's quite profound and quite philosophical. Yeah, and that's it. That's all there is with gravity. So GMM over R squared can actually explain why life on Earth was able to be possible. Okay, that's all there is for dynamics. Thanks for coming out. Thanks for sticking around for an extra 15 minutes. I told you it wasn't going to be too long. I encourage you to go back and read the typed notes and do some practice. For people watching on YouTube, I will see you on Monday. So I'll stop the recording now and I'll briefly look at the chat.